Welcome to this explainer. I am absolutely pumped you're here today because we are tackling what is, honestly, the darkest and most compelling mystery in the entire universe. Just imagine, for a second, falling toward a black hole. As you get closer, gravity gets stronger and stronger, until you hit this boundary. Cross it and there is absolutely no way back. Not even light can escape. But what if we flip the script entirely? What if instead of pulling everything in, there was an object out there that literally only pushes things out?
Okay, let's dive right into this crazy dichotomy. On one hand, we've got the black hole, right? The ultimate pole. Gravity traps matter and energy and nothing escapes. We know for a fact they exist. But then, on the flip side, we have the white hole, the ultimate push. It's this mind-bending theoretical object where matter and energy can only exit and absolutely nothing can enter. We have never actually seen one. So, what exactly is the difference here? And could these two bizarre cosmic objects actually be connected?
Section 1. The darkest cosmic mystery and how black holes work.
So the defining feature of a black hole is the event horizon. And it is exactly what it sounds like, the absolute point of no return. Down at the center is what scientists using classical general relativity call a singularity. And surrounding that singularity is the event horizon. Think of it as a strict one-way entrance. Once anything crosses that boundary, well, according to general relativity, it's trapped. It cannot escape back into our universe. And since that includes light, the whole thing is completely dark to us, hence the name black hole.
Now, it's probably worth a quick reminder here that black holes aren't just giant cosmic vacuum cleaners roaming around relentlessly sucking up everything in the universe. Actually, if our sun were somehow magically replaced by a black hole with the exact same mass, Earth wouldn't suddenly get sucked in. No, it would just keep orbiting it almost exactly as it does right now. The gravitational mechanics work the exact same way. Literally, the only difference is that our sky would go completely pitch black because, well, no sunlight. The real danger only kicks in when you get extremely close to that event horizon we just talked about.
But how do these gravitational monsters actually form? Well, it's a spectacularly violent, chronological process. Step 1. A massive star spends millions of years churning out energy through nuclear fusion. And this energy creates an enormous outward pressure that perfectly balances the inward pull of the star's own gravity. But then, step 2 hits. The fuel runs out. That outward pressure just drops. Step 3. Gravity instantly takes the wheel, and the core collapses incredibly fast. And finally, step 4. The outer layers of the star explode in a massive event that we call a supernova. If the core that's left behind is massive enough, that collapse just keeps on going until it forms one of the most extreme objects in the universe, a black hole.
And they definitely don't just come in one size. To get a true sense of the sheer cosmic scale we're dealing with, we start with stellar mass black holes. These are several times greater than the mass of our sun. Then, we step it up to intermediate mass black holes, which kind of bridge the gap between the small ones and the giants. And then, we have the absolute titans, supermassive black holes. We're talking millions or even billions of times the mass of our sun. Just staggering.
Which brings us to a really massive number, 4 million. Right at the center of our very own galaxy, the Milky Way, sits a supermassive black hole named Sagittarius A star, and it has a mass roughly 4 million times greater than our sun. I mean, it is unimaginably huge. But thankfully, despite all that enormous mass, it sits incredibly far away from Earth, so we are perfectly safe.
Section 2. The white hole theory.
Think about it like this. A white hole would be like a one-way exit. Things could leave, but nothing could enter. A white hole is quite literally the exact mathematical opposite of a black hole. Where a black hole is a one-way entrance, a white hole is a strict one-way exit. And this fascinating idea doesn't just, come out of nowhere. It actually pops right out of the mathematical solutions to Einstein's equations of general relativity.
But that brings up a really crucial question, doesn't it? If the math of general relativity works for white holes just as well as it does for black holes, why haven't we ever found one? I mean, we have immense observational evidence for black holes. We've detected their effects on nearby stars, we have observed gravitational waves from them smashing together, we've even snapped pictures of their shadows. But white holes? Literally nothing.
Well, the answer lies in a pretty fundamental scientific truth. Mathematics doesn't automatically mean nature actually creates the object. Equations might allow for a certain solution on a chalkboard, sure, but the real universe might never actually produce it. Just think about it. A white hole would have to spout matter out while absolutely forbidding any matter from entering. We know the natural process of a collapsing star that creates a black hole, right? But we do not know of any realistic natural process that would create a stable white hole. That missing origin story is honestly one of the biggest reasons scientists remain highly skeptical that they actually exist.
Section 3. Can they be connected?
To answer that, we really have to look at a massive clash between the two fundamental pillars of modern physics. General relativity beautifully describes gravity in massive objects like stars and galaxies, and then quantum mechanics perfectly describes the microscopic world of subatomic particles. The problem? Well, at the very center of a black hole, conditions are so unimaginably extreme that these two theories just clash. Our current understanding completely breaks down. We simply don't have a complete picture. To truly understand what happens inside, we desperately need a theory of quantum gravity.
And this is where theoretical physicists propose something absolutely amazing. Because our classical math breaks down at the singularity, some highly speculative models suggest that a black hole might not end in a true singularity at all. Instead, quantum effects could potentially step in and halt the collapse of all that matter. In some of these models, the black hole essentially bounces and transitions, eventually behaving exactly like a white hole. It's an incredibly fascinating concept, but, and this is a big but, it is absolutely vital to remember this is purely theoretical physics right now. There is zero confirmed evidence that this transition actually happens.
And that brings us to yet another mathematical marvel, the Einstein-Rosen bridge. Though you probably know it by its much more famous name, a wormhole. In some mathematical solutions to Einstein's equations, a black hole and a white hole actually appear together, linked by a hypothetical tunnel through spacetime. It basically paints a picture of a cosmic subway system. You enter the black hole side, travel through the tunnel, and theoretically emerge out of the white hole side in a completely different region of space and time.
Wild, right?
I know. It sounds like perfect science fiction, but let me quickly bring us back down to reality. Even if these structures do exist in the math, the simplest versions of these wormholes are absolutely not considered traversable. They are incredibly unstable and would collapse way too quickly for a person or even a spacecraft to travel through them. We have never observed a traversable wormhole. So once again, the math is totally fascinating, but the physical evidence just isn't there.
Section 4. Reality versus theory. So, to sum this all up, black holes trap matter, white holes repel it. Black holes are a one-way entrance, white holes are a one-way exit. But the most vital distinction here is their actual status. Black holes firmly belong to established observable astrophysics. We've got the data, we've seen the shadows, we've felt the gravitational waves. White holes, on the other hand, remain purely theoretical. They're this incredibly fascinating possibility allowed by our current math, but they are utterly absent from our telescopes.
At the end of the day, we still don't completely understand what happens at the very heart of a black hole, where all of our theories break down. Maybe future discoveries will prove white holes are completely impossible. Or maybe they'll reveal that black holes truly do transform into them. Or perhaps nature has something even stranger waiting for us. For now, the universe is still keeping its ultimate secrets strictly under wraps. So the next time you look up at the night sky, I really want you to ask yourself, what other mind-bending secrets of space, time, and reality are hidden right beyond that event horizon? Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll see you